So what we discussed in the previous class. In the previous class, we were doing some problems based on right? Only problems over. And Boolean to mass circuit. We calculated what is the acceleration. We calculated it. I told you about output function. So with that, we are actually done with the part of the free body diagram and the Newton's law of motion. So now we will concentrate on the next topic called right. So we'll be concentrating on the term friction. Okay, let's see what it actually means. Suppose I have a fixed surface on which there is a book kept, or there is a block of mass that is kept, right? Now, when I apply a force on that particular material, what will happen is, though I apply a non-zero force, sometimes you can observe that the object will not move. Right? For example, I have my mobile like this. Right? There is a fixed surface. Let's say I'm tying it to a string and trying to pull it. So I'll give a non-zero force, but to my surprise, I can observe that this object will not move at all. And why is this happening? It is because there is some other force which is coming to existence due to the surface in which my mobile phone is in contact. Right? Which is actually trying to oppose the cause that I'm trying to produce. So I am the cause. I'm trying to apply an action, and there is a reaction in the opposite direction, which is actually not making this object. Right? So that kind of reaction force, which is generally resistive in nature, right? Which stops the motion of an object, is what we call it as friction. Right? And friction is represented with the symbol small f. So when you draw the free body diagram, what happens is capital F is applied in the rightward direction, and small f starts acting in the leftward direction. Are you able to understand? Right? And why is this happening? And why is this kind of a force even coming into existence? It is because there is an interlocking taking place between the surfaces in contact. Means if there is one block on top of which, right? So there is one block and there is another object which are in contact with each other. Generally, what happens is, to our naked eyes, it will appear as if they both are smooth in nature. But in reality, what will happen is there will be some amount of irregularities which are present in this way. So this is for object 1 and this is for object. So object 1 and object 2 will be rough in nature, due to which there will be an interlocking, and one will try to oppose the motion of another. Are you able to understand what I am trying to say? So from this, what we can say is friction is. So if I try to give a definition to what is friction, friction is a force that actually reduces the relative motion between two objects. So friction is a force that reduces the relative motion between two objects. So what do I mean by relative motion here is, observe. Suppose I take this and I try to move this object, right? So when I'm trying to move this object, there is a force exerted by my hand on this remote control, which is in this direction. But at the same time, the remote control will also try to exert a force on my hand in rightward direction. So if my hand is exerting a force on the remote in the leftward direction, which is trying to oppose the external force that is trying to pull it, right? The remote will try to apply the force on my hand exactly in the opposite direction. Meaning, if you draw the free body diagram of both the objects, so here what I did is I drew the free body diagram of only the block in which it was in contact with, right? If I draw the free body diagram of the surface also, then what I could have observed is on the surface, due to the block, there would have been a force in the rightward direction, which is exactly of the same magnitude. That is why I told there is an opposition taking place in the relative motion between the objects. And this kind of a force is again called as an action reaction pair. So basically, when you talk about friction, friction is an action reaction. So here, make a note of this. Okay. So the question is parameters on which the frictional force depends. Right? Say factors on which frictional force depends. So if you observe an object experiencing a frictional force small f, then that small f is observed to be directly proportional to the normal offered by the surface. Means, if I try to draw the free body diagram, mg will be in the downward direction and normal will be in the upward direction. So what I'm trying to say is, frictional force is directly proportional to the normal offered by the surface. Here comes an important question. So, if this diagram, if you see, the normal force is actually equal to mg only because vertically there is no force acting, right? If that is the scenario, why didn't I use a word that frictional force is dependent on the weight of the object? Rather, I'm using the word that the frictional force is dependent only on the normal offered by the surface. So why am I doing this? Answer is very simple. If you see, friction is offered by whom? By the surface in which the object is in contact with. So what is the reaction force the surface is offering? It is normal. Mg is the action it is taking, right? It is being subjected to an action of weight, whereas normal is the reaction offered by the surface. So that is why whenever you try to express it, you should always write that the frictional force is directly proportional to normal because both are properties of the surface of contact. But mg is not the property of the surface of contact. That is one reason. And secondly, you see, The same object is placed on an inclined surface like this. It has a mass here. Here it is mg. Here it is mg sin theta. Here it is mg cos theta. Right? And the normal force will be like this. Right? So in this case, how will it act? So the frictional force will be in this direction. In this scenario also, if you see, you should write that the frictional force is directly proportional to normal only. Why I told us? In this case, n is equal to mg, weight. Whereas when the object is placed on the inclined plane, the normal is not equal to mg, rather it is equal to mg cos theta. Right? So when you write this, you're saying that the frictional force is directly proportional to the normal force. Means whenever a proportional symbol is there, you need to remove it and introduce a constant of proportionality. So the constant that we are going to introduce is called as mu. So it's pronounced as mu, which is mu. Okay. So F is equal to mu times capital N, where this mu is called as the coefficient of friction. So it is called as a coefficient of friction. Shall I proceed? Now, we are going to discuss a very important point, concentrate. We are going to discuss about the different types of friction that are available. Okay. So the first one is called as static friction. Okay. So what is static friction? This is now this object is there. I am applying a force on it, right? I am applying a force on it. It is not moving. Let's say I apply a force of 1 Newton. It is not moving. I am applying a force of 2 Newton. Still not moving. 3 Newton not moving. Like this, I keep on doing it till 5 Newton. Okay. So when I applied 5 Newton, I could see that the object started moving. So till that force of 5 Newton was obtained, what was actually happening to the object? The object's motion was completely resisted by the surface which was in contact with it. Right? Means whatever is the force you applied, if it was below 5 Newton, the surface did not allow the object to move at all. Am I right? Right. So that friction which comes into play when the object is at rest is called as static friction. Right? So if I have to give the simplest definition, you call it like this. Friction that comes into play when the object is at rest. It's called as static friction. Am I clear with this point? Now listen to this. So I told you, till you reach a particular limit, in the example that I discussed, till you reach the limit of 5 Newton, you could observe that the object was stationary, right? But the frictional force was existing, right? So what can you say that the maximum value of the frictional force which can stop the object from moving? It was 5 Newton, because immediately the moment you apply value greater than 5 Newton, the object started moving. Means the surface could not hold it back, right? So what we can say is, there is only a certain limit to which the surface can offer a force on the other object in terms of friction. So that is static friction just before it starts. So just before the object starts, and I repeat it, just before the object starts, there is only a certain limit to which the surface can offer resistive force to the object, right? And that value is called as the limiting value of static friction. So why it's called as limiting value is because that is the maximum limit to which it can hold. But you can ask me a question, what is going to happen till then? So what is the limiting value in our example? It was 5 Newton, right? When you applied 1 Newton, what is the limiting value the surface can offer according to the concept that we know already? It is 5 Newton. But the surface will not bring in all the 5 Newton into picture. So when you apply 1 Newton, the surface will also start offering exactly 1 Newton, because it knows that if I apply 1 Newton itself, the object is not going to. When I increase it to 2 Newton, this will also apply only 2 Newton. When I increase it to 3, 3, 4, 4, 5, 5, 5.1, this is still going to be 5 only. Because it has reached its limiting value. Limiting value is the maximum value. Are you able to understand? So till that limiting value was obtained, the static friction is able to adjust itself. Are you able to understand the concept? So depending on the external force you applied, which is lesser than the limiting value, the surface started adjusting its static friction value. That is why static friction is also called as self-adjusting force. It's called as self-adjusting force. So in this context, I explained two things. What are they? One is called as limiting friction, and the second point is static friction is a self-adjusting force. So static friction is a self-adjusting force. This is one point to be noted. And the maximum value of static friction before which the object does not move. Before which the object does not move is called limiting friction. It's called as limiting friction. So if I write F, small f represents friction. If I put a subscript L, it is written as limiting friction. So Fl is written as mu s into n. So we know that small f is equal to mu into n according to the previous discussion. But here what I am trying to say is L stands for limiting value is equal to mu into S stands for static value times capital N. Right? And this is going to be the mathematical expression for limiting friction. Shall I proceed? Now the question is, once the static friction, once the limiting value is exceeded, what happens to the object? The object starts moving. So you apply a force 5.1 Newton, the object started moving. But here comes another question. So when the object is moving, is the object still experiencing frictional force or not? Yes, it is experiencing. But this time, it will be lesser than the value that was offered before the object started. right? Why is it so? Because I told you the cause for friction is the interlocking that is taking place. What happened? The interlocking. So when the object is at rest, the interlocking can be intact. Right? It can be acting for a stronger value. Whereas once it starts moving, you're not giving the object sufficient time to get interlocked. Because different surfaces will have different kinds of irregularities. So when it is moving, you're not giving sufficient time for it to get interlocked, as a result of which here also frictional force is going to act, but it will be lesser than that of the limiting value. And this kind of frictional force that comes into play when the object is in motion is called as kinetic friction. Okay. So the second kind of friction that we are going to see is called as kinetic. So how do you define it? It is a frictional force that comes into play it is a frictional force that comes into play when the object is moving. So frictional force that comes into play when the object is moving is called as the kinetic friction. Done? No. Now what will happen is, if you write the value of kinetic friction, if you write it as Fk, then that Fk will be equal to mu k into N, where K stands for kinetic. Okay. So Fk is the kinetic friction, mu k is the coefficient of kinetic friction, and N is a normal. Okay. And third kind of friction that we are going to discuss now is called as rolling friction. So, if I, for example, I take this bottle cap, right? If I say it is revolving like this, right? It is revolving like this. What will happen is, here also it is moving. When I say revolving, it is revolving, actually it is having revolution and translation. So it is actually rotating on my hand. Are you able to understand this? Right. When this kind of a scenario arises, we are able to see that the point which is there in contact is changing for every instant. It is not the same point that is in contact. So compared to the previous situation of completely translatory motion, which was kinetic friction, here if you see the object is rolling, no, at that point, since the point of contact itself is going to be very less, and you are giving even more lesser time for the interlocking to take place, then third kind of friction that comes into picture is called as rolling friction. So the friction experienced by the object when the object is rolling is called as rolling friction. So when you talk about this rolling friction, Fr will be equal to mu r into. So R stands for rolling. So Fr will be equal to mu r into N. Okay. So when you do a comparative study, limiting friction is greater than or equal to the static friction is greater than the kinetic friction is greater than the rolling friction. So what happens here is US is definitely greater than UK is greater than UR. Means in a problem, if they are given you two coefficients of friction, then by looking at the magnitudes of both, you can decide what kind of coefficient they are trying to talk. So the one which is going to have the greatest values for the static, followed by kinetic, followed by cold. So the next concept that we are going to discuss is called as angle of friction. Angle of friction is represented by a symbol lambda. Suppose I have an object lying like this, and there is an external force capital F that is applied, and the frictional force comes into picture in the leftward direction. Then there is going to be a normal force like this, right? So here you have normal force. If I draw all the vectors associated, we have the normal force in the upward direction, frictional force in this direction. Then these two forces have a resultant in a particular direction, right? They have the resultant in a particular direction. If we call that resultant as capital R, then the angle made by, listen to this carefully, the angle made by the resultant of normal and frictional force with the normal itself. So angle made by the resultant of normal and frictional force with the normal itself means, if I am able to define this angle is called as the angle of friction. So the definition is angle made by the resultant of normal and frictional force with the normal itself is called angle of friction. Right? So if you observe this scenario, listen to this. If you observe this scenario, then I can define tan lambda according to vectors. So tan of this lambda is going to be equal to opposite divided by adjacent. So F divided by capital F. So tan lambda will be equal to F divided by capital F. But we know that F is equal to mu into N divided by capital F. So N and N will get cancelled. From this, what can I conclude? From this, we can conclude that tan lambda is equal to mu. So we can conclude that tan lambda is equal to mu, or the conclusion I can draw is tan lambda is equal to mu, or lambda is equal to tan inverse of . So the angle of friction is found using this mathematical expression, tan inverse of mu, where mu is the coefficient of friction that will be given. the point here, you can note it. So we'll see what is the next concept. Okay. So the next concept is called angle of reverse. Okay, which is represented by the symbol alpha. Now observe this. Suppose I have a surface like this, right, on which I'm keeping an object. Right? What are you able to see from that side? You'll be able to see this line, and you'll be able to see the cross-sectional view of this particular surface, the shape of a rectangle. Right? Now, what I'll do is, I'll keep the bottom surface fixed. I'll slowly start lifting this. So, what is happening after a certain point? So, initially, if you see, this part is there, which is movable. So, initially, this part is there, which is movable. I can rotate it actually, right? So, initially, this was making an angle 0 with respect to the horizontal. So, when you started making it get inclined along with the surface, you could see that the object started sliding. So, that object starting to slide, there will be one initial point, right? So, during that initial point, what would have happened is there would have been an angle made by the surface with the horizontal. So, the angle made by the surface with the horizontal at which an object starts to just slide is what is called as angle of reverse. So initially, why did it slide? When I took it like this, it did slide because it was having mg cos theta in this direction, but frictional force was also acting in the opposite direction. I'm sorry, it had mg sin theta in this direction and frictional force in this direction. Right? But after a certain point, what happened? Mg sin theta started dominating the frictional value and it started sliding. So angle of reverse means angle made by a surface with the horizontal at which it just begins to slide, by overcoming the frictional force called angle of force. So, if I take the object and place it on top, if I take this to be alpha, at which the object starts to just begin sliding, okay? Here, if it is mg, then this will be mg sin alpha. Here it will be frictional force, and here it will be normal. Right? For the object to just start sliding, what should happen? Mg sin alpha should be slightly greater than frictional force, right? Should be slightly greater than F. So what I'm trying to say is the limiting value or F should be equal to mg sin alpha for this kind of a scenario to occur. So what is going to be the value of F? F is mu into n. So F is how much? F is mu into n. So when I write F is equal to mg sin alpha, mu into n will be equal to mg into sin alpha, which implies mu into what is the value of n? N is going to be mg cos alpha is equal to, this will be mg sin alpha. So mg and mg will get cancelled, which implies u will be equal to sin alpha divided by cos alpha, or I can conclude u is equal to tan alpha, or I can conclude that alpha is equal to tan inverse of u. So if you observe this, then you can understand that angle of repose is numerically equal to the angle of friction. So, angle of repose is numerically equal to the angle of friction. Are they both the same in terms of context? But they are numerically the same value, because angle of friction can be defined even on a horizontal surface, whereas angle of repose can be defined only on an inclined surface. Are you able to understand this point? There is a very, very important point to be able to make it. Can we start with some problems? So there is a particle of mass 1 kilogram that rests on rough contact with the plane inclined at 30 degrees to the horizontal. Inclined at 30 degrees to the horizontal, and is just above this level. Find the coefficient of friction between the plane and the particle. All right, sir. The problem. Okay. So did you read the question? So it says, a particle of mass 1 kilogram rests on a rough contact with plane inclined at 30 degrees to the horizontal and is just about to slip. Find the coefficient of friction between the plane and the particle. Right. So when you see the word, it is just about to slip. When will this happen? During the condition of angle of repose. So just now we saw mu is equal to tan alpha. So here alpha is what is the angle of repose, that is 30 degrees. So mu will be equal to tan 30, which will give you 1 by root 3, and that is the required answer. So mu is equal to 1 by root 3 is the coefficient of friction of the surface on which this object is placed. The next question is number 2 is figure shows two blocks in contact sliding down and inclined surface of inclination 30 degrees. The coefficient of friction between the block of mass 2 kilogram and the incline U1 is 0.1, and that between block of mass 4 kilogram and incline U2 is 0.3. Find the acceleration of 2 kilogram block, and the value of G is 10 meters per second square. So the diagram is like this. This 4 kilogram, 2 kilogram block, the angle of inclination is 30. So there is a 4 kilogram, there is a 2 kilogram block, both are in contact with each other, and the angle of inclination is 30. So based on this scenario, we need to find the acceleration of the 2 kilogram block. So if you see this question, right? Our job is to calculate the acceleration of the 2 kilogram block, right? So for that, what I will do is, first thing that we need to understand is this 4 and 2 kilogram block both will move the same acceleration because they're always in contact with each other, right? So what is going to be the net force acting in the downward direction? So this is called as downward direction, and this is called as upward direction. So the net force acting in the downward direction is how much? It is m1g sin theta plus m2g sin theta. So if you see g sin theta is common, g sin theta into m1 plus m2, which implies g is how much? 10 into sin 30 is half into m1 plus m2 will be 6. So if you get cancelled, you will get 30 Newton. So 30 Newton is a force that is acting in the downward direction. Okay. But what is the force acting in the upward direction? So upward direction is there are two frictional forces. One frictional force is on 4 kilogram and the other frictional force is on the 2 kilogram. So this will be equal to F1 plus F2, where F1 will be U1 into N1 plus F2 will be U2 into N2. Right? So here it will be U1. U1 is how much? The force between 2 kilogram and the incline is 0.2. The coefficient of friction is 0.2. So 0.2 into N1 is how much? N1 will be M1g cos theta. So 2 into g into cos 30 degrees. Plus what is the value of U2? U2 is going to be 0.4 into 4 into g cos 30. Right? So this will be 0.4 into 10 into cos 30, that is root 3 by 2, plus 1.6 into 10 into cos 30, that is root 3 by 2. So what is going to be the answer? Simplies it be 4 plus 16, that is 20 into root 3 by 2, or it is going to be 10 root 3. So 10 root 3 is going to give us 17.32. So what I'm trying to say is, the net downward force acting is 30 Newton and the net upward force acting is 17.32 Newton, and these two blocks are supposed to overcome the resultant of these two. So 30 minus 17.32, and that should be equal to mass into acceleration. So what I will write is net force acting on the object is 30 minus 17.82. So you get 0.68 and 30 minus 17, 29 minus 17 is going to be 12. It is 12.68 Newton, and this 12.68 Newton should be equal to the net mass multiplied with acceleration. 12.68 is equal to net mass acting on the object is 6 multiplied with A, which A will be 2.11 approximately meter per second. It's approximately this value. Okay, we can open. Is that okay? So let's see. Example number. A 70-kilogram block is pulled by a 400 Newton force at an angle of 30 degrees to the horizontal. The coefficient of sliding friction is 0.5. Find the acceleration of the box. The G will be equal to 10 meters. Okay. Here, what do I mean by sliding friction? Sliding friction is kinetic friction. Okay. If you observe, the diagram, it looks like this. There is a box, 70 kilogram mass, and there is a force of 400 Newton, which is applied at an angle 30 degrees with respect to the horizontal. Right? So this 400 can be resolved into two components. One is 400 cos 30, and the other is 400 sin 30. And remember, there is mg acting downwards, and there is a normal force also acting in the upward direction. Okay. And remember, there is a frictional force that is acting in the opposite direction, which is the sliding friction. So, the net force acting on the object is going to be 400 cos 30 minus F is equal to mass of the object into its acceleration. So 400 into cos 30 is going to be 3 by 2. Minus F is Q into the normal forces that are acting in the upward direction. So what are the upward forces that are acting? N plus 400 sin 30. That is mg plus 400 sin 30 is equal to mass of the object, that is 70, into its acceleration. So when you try to calculate this, this will be 200. So 200 minus mu is half into mg is how much? Mg is 700 plus 400 into sin 30 is half will be equal to 70. So cancel this 200 times. So this whole thing will get cancelled 450 times. 200 root 3 minus 450 will be equal to 70. Which implies 70 implies A will be equal to 200 root 3 minus 450 by 70. These many meters per second square will be required. I'll experience some problems that are based on equilibrium of all forces. Okay. So first we need to understand what does equilibrium mean. So when I talk about equilibrium, there are two kinds of equilibrium. One is called as static and the second is called as dynamic. Listen to this. Suppose this object is there. Okay. If I'm disturbing the object from its equilibrium, if I disturb it like this, if it is coming back in the path, if it is coming back reverse in the path in which it was disturbed. Okay. So when I disturb, its equilibrium got disturbed. Whereas so equilibrium is basically when all the forces, that is translatory forces and the rotational forces are balanced. What are those rotational forces? I'll tell you later. That is called as torque. But as of now, understand that when all the translatory and the rotational forces are balanced, the system is said to be in equilibrium. Suppose you take this object, this is said to be in equilibrium. So when I disturb the object from its equilibrium position and when I release it, okay, if it is revolving back in the direction in which it was disturbed, means if it follows the exact path in which it was disturbed and coming back to its original position, we call it as static equilibrium. Whereas when you disturb it and it takes 180 degrees turn and then comes to equilibrium, then you call that as a dynamic equilibrium. Are you able to understand? So static means when the object is disturbed, it should traverse back in the same path along which it was disturbed and come back to its original position. Whereas in the dynamic equilibrium, it takes a turn of 180 degrees and then comes to equilibrium. Okay. So what does equilibrium mean here? Equilibrium means all the forces are said to be balanced. What forces? Rotational and translational forces are said to be balanced. Now we'll do some problems that are based on this equilibrium of forces. So based on equilibrium of forces, let's consider an example one. The question says, determine the tensions T1 and T2 in the strings. So this is how the system is, and the system is balanced. Now we need to calculate the tensions in the system. So how do you do this? When you divide it into multiple parts like this, right? So if this is 60, this will also be 60, alternate interior angles. So this T1 can be resolved into two components as T1 cos 60 and T1 sin 60. Right? So the system, when it is balanced equally in the horizontal direction and in the vertical direction. So along the horizontal, if you see, along the horizontal, all forces are said to be balanced. So T1 cos 60 degree will be equal to T2. So T1 cos 60 will be equal to T2. Similarly, along vertical direction, all forces are said to be balanced in the sense P1 sin 60 could be equal to mg. So P1 sin 60 could be equal to 400. Okay, I'm not writing this. We take it as 400. So what can we conclude from equation 1 and equation 2? When I divide 2 with 1, then I'll get sin 60 divided by cos 60 is equal to 400 divided by 80. So sin 60 is half, cos 60 is root 3 by 2 is equal to 400 divided by 80. 2 and 2 will get cancelled, which implies P2 will be equal to. Oh, I sorry. Coming from here. So which implies sin 60 is root 3 by 2, cos 60 is half is equal to 400 divided by 80. So 2 and 2 will get cancelled. So we can conclude that T2 is equal to 400 divided by root 3, which is equal to 400 root 3 divided by 3. Okay, so when you rationalize it, T2 will be equal to 400 root 3 divided by root 3. Now, if I take this and substitute it in 1, using 3 in 1, we will get T1 cos 60 is half. Cos 60 is half is equal to T2 is 400 root 3 divided by 3, which implies T1 will be equal to 800 into root 3 divided by 3. If you observe, T1 is exactly twice that of T2. Right? So this is how you find both the forces. one last problem based on clear. Example 2. Right. So example 2 says that there is a ball of mass 1 kilogram which is hanging in equilibrium from two strings OA and OB. Yeah. So what are the tensions in the string OA and how to do this? Shall we see? So this is 120, this is already 90. Right? If this comes out to be 90, how much will this angle be? This angle will be 30 degrees. Right? Now this P1, if it is resolved into two components, P1 cos 30 and P1 sin 30 in this direction. And P2 is like this. Say out of this 60 is then P2 cos 60 and P2 sin 60. So if you observe, P1 sin 30 is in upward direction, P2 sin 30 is or sin 60 is also in upward direction, P2 cos 60 is in the rightward direction, and P1 cos 30 is in the leftward direction. P1 cos 30 is the leftward direction. So P1 cos 30, which is the leftward direction, is balanced by P2 cos 60. Right, that is one. Similarly, T1 sin 30 plus T2 sin 60 is balanced by W. So T1 sin 30 plus T2 sin 60 is balanced by W. So from 1, what I can conclude is T1 into cos 30 is root 3 by 2 is equal to T2 into cos 60 is half. So it both will get cancelled, which implies T2 is equal to 3 T1. If I take it as 3, I'll take this and substitute it here, which implies T1 into sin 30 plus T2 is root 3 T1 into root 3 by 2 is equal to W. But what is the value of W? It is 10 because 1 kilogram into G. So T1 by 2 plus T1 by 2 is equal to 10, which implies 4T1 is equal to 20, or implies T1 is equal to 5 Newton. So tension in string number 1 is going to be 5 Newton. If you take this 5 and substitute it here, then T2 you will get it as, then T2 you will get it as 3 times 5, or T2 is equal to 5 root 3. So So tension 1 is 5 Newton and tension 2 is 550. Is it clear? Okay. So we saw different kinds of problems, right? Right. So we saw different kinds of problems where we had different strings which are connected to the same point. So that point is called as concurrent point. Okay. There is a point on which multiple forces are acting, and the forces are acting in such a way, that the whole system is said to be in equilibrium. So what do I mean by equilibrium? The whole system is said to be balanced, right? Then let's say the angle between the forces are alpha, beta, and gamma. Okay. If the angle between the forces are alpha, beta, and gamma, like this. Then under balanced condition, you can say that a force divided by sine of the angle opposite to it. That is F1 by sine alpha is equal to the other force divided by sine of the angle opposite to it. That is sine beta is equal to F3 divided by the sine of the angle that is opposite. That is sine gamma. And this is a condition which can be obtained under equilibrium scenario. And this has the name called as Lammy's theorem. So from next time onwards, instead of you trying to resolve it into different free body diagrams or different vectors, right? Instead of you resolving it in different vectors, you can use this particular expression to solve the problem, so that you will get the answer in one step. Right? I hope it is clear. Okay. So today's concepts that we discussed are based on complete friction and equilibrium of forces, right? So there are two more subtopics that are left out. One is how will friction help the objects take turn on the road? When a car is taking turn on a level road and on a road called as bank road, how will friction help? So there is a derivation which is very, very important in exam perspective. The derivation comes always. And sometimes they ask you the problems also. So you need to understand the concept. So that will be the concept with which we're going to start tomorrow's class. So I just wanted to find out one thing. Tomorrow, can we have an early class? 5:15, 5, is it possible? Can you all come by 5? You have to tell me soon. I have to decide. No? Those who are online, is online. Around 5:15 at least. Can we do that? That will work? 5:15 will work, 15 minutes will go. Okay. So tomorrow's class will start at 5:15. We'll have till 6:45. Okay. So revise these concepts. These, as I told you, these are all important. And in tomorrow's class, I'll explain the circular motion. So I hope it's clear. And remember, I asked you for reviews. You guys, remember, I didn't send you the link to the station. So can you guys help me today? I'll share it with you. Yes. Guys, we'll wind up. Those who are online can leave.
Thank you.
Thank you, sir.